All right, hello again, everyone. This is Professor Brian Macon coming to you live from the Department of Integration. Well, again, I guess I'm not really live, am I? I mean, you're watching me recorded. But all right, you understand what I'm saying. So in this section, this is the last video we're going to cover here on techniques of integration, if you will. And we're not really doing a technique of integration in this section. However, we are discussing what we call an improper integral. So if you think about an improper fraction, like an improper fraction of 3/2, we write as 1.5. So in these improper integrals that we look at, we're basically going to convert them to a proper integral, if you will, and then evaluate them in a slightly different manner. So all right, before I get too far down the road here, let's talk about conceptually what an improper integral really is, and in a visual manner. I like to look at this in a visual manner. So for example, let's say we look at the function 1 over x squared. So I'm going to graph y equals 1 over x squared. Looks something like this. Here's 1 over x squared, right? Now let's suppose, I propose to you that we're finding the area under the curve from 1 all the way out to infinity. So we're looking all the way out to infinity here. So we're finding the area under the curve all the way out to infinity. So that is basically a visual interpretation of what it means for this integral to be improper. So I'm looking at the area under the curve of 1 over x squared from 1 to infinity. Usually, kind of a shortcut, we can look at the limits of integration. We can see an infinity here, and we can say, well, hang on a second. We're not supposed to be able to, integrate to infinity. So that signals that it's improper. But the real reason that this is improper is we have what would appear to be infinite area. And what we're going to notice by the end of this video is that sometimes that area is infinite and sometimes it is not. And we'll talk about maybe a couple conditions why that's the case, right? How could it be possible that that area is finite? Because it looks infinite. So here's our concept of what we're going to do here. So if I were to go ahead and attack this problem and work it out, what I'm going to do, let me change colors here. And let me go to black. And so because we can't really go to infinity, what we're going to do is back away, and we're going to pick some number t. And then remember, one of the most beautiful aspects of calculus that we have used as a wonderful tool is the limit process. So, technically what I'm going to do is I'm going to integrate from 1 to t, and I'm going to treat t as a constant value conceptually. But then, at the end of evaluating this integral with this constant number t, I'm going to then come back, and let me write that as black. We're going to take a limit as t goes to infinity. So this will be the last piece of our work when you evaluate these integrals. So, let's just go ahead and complete this example here. So I'm just going to kind of come over to the side. I'm going to do, a little bit of side work. So let's integrate from 1 to t, 1 over x squared dx. So that's equal to, negative 1 over x from 1 to t. And then this is negative 1 over t minus negative 1 over 1. So this integral turns out to be negative 1 over t plus 1. All right, now let me come back here and put in my limit, because I really have the limit process going on at the end of this. So I have the limit as t goes to infinity, right? Now, you should have learned in a calculus course, right, that when I have 1 over something that grows without bound, right, so t goes to infinity, that this whole fraction tends to 0, goes to 0. If you think about this numerically, 1 over 10 is 0.1, 1 over 100 is 0.01, 1 over 1,000 is 0.001, right? So just numerically speaking, we can see that this is going to 0. So I'm getting this guy going to 0. So I'm getting, let me say, 0, right, plus 1. So as it turns out, this is pretty cool. What looked like infinite area under the curve of 1 over x squared really is finite. It's really 1 in the limit process. Now, one thing we could do here, real quick to explore numerically, right, is let's say I do this. Let's say I'm going to go to my y equals equation, and I'm going to integrate. So on the TI 84 calculator, I do math, and then number 9 is the function integrator. And then I'm going to integrate, let's say, from 1 to x. So I'm going to use the letter x. The reason I'm going to use the letter x is because my calculator, and when I go to the table, x is the variable. Right? Now, because I'm using x here, technically, mathematically speaking, what I need to do is use a different letter inside the integral. Right? So usually what you'll see most calculus textbooks do is they'll use the letter t. So I'm going to do alpha 4, and I'm going to put t raised to the negative 2 power, and then dt. So technically I can't have the same variable in the integral and the limit of integration. So whatever, this is 1 over t squared dt as we go from 1 to x. And so when I go to the table, so I'm going to do this first. I'm going to do second window and go to the table set menu. And I'm going to make the independent variable the ask option. So then when I go to the table, it's blank and I can plug values in. So keep in mind I integrated from 1 to x. So I'm going to let that x go to infinity. So the integral from 1 to 10 would give me 0.9. The integral from 1 to 100 would give me 0.99. The integral from 1 to 1,000 would give me 0.999. And the integral from 1 to 10,000 would give me 0.9999. At some point, my calculator is going to be like, all right, you know what? I'm just going to round to 1. Right? So let me see what happens if I do 100,000. That's probably what I'll get. And it takes a little longer each time for the calculator to evaluate this. All right, it's like, screw you, this is 1. So if I come over here and highlight the number, you can see it isn't really 1, but it's rounding, right? So it keeps all that decimal accuracy. But numerically speaking, we can see as the upper limit of integration goes to infinity, the integral goes to 1. And that's what we saw in the actual limit process. So it's pretty cool. I mean, that's really cool. I mean, the first time I saw that, it was like, my brain exploded. This is awesome, right? So how could possibly infinite area actually be finite? Well, good question. Let's not delve towards the answer there. So just yet, right? So in this section, you're kind of exploring, right? You're looking at some integrals that are improper. And you're finding some scenarios where that integral is actually finite in value and where it's infinite. Now, usually in this section, they would introduce to you, right, an author of a textbook, right, or I'm telling you that we introduce 2 new terms, and one is called convergent and one is called divergent. So if this improper integral has a finite value, right, in other words, if the limit exists, then we're going to say the integral converges. And those are the cases, when I get a finite answer out of my limit, right? And then if this limit, right, is infinite or doesn't exist, right, then we say the integral diverges. So we're going to use that terminology here, and I'm going to say, thus, the integral converges. Now again, we could interpret this visually as an area. Right? So, in a visual manner, I like to look at the integral as being an area, although that's not technically what it always represents, right? Integrals can be volumes inside a curve. Integrals can represent surface areas. Integrals can calculate work done, right? So, I mean, I can use integrals in a lot of different applications, but, conceptually, an integral we could think of as an area. So that's how we're going to represent it through our conversation here. All right. Now, let me come back up to the original graph that we sketched real quick. And let's just talk about this idea of being improper again. So technically, an improper integral is an integral where visually I might have infinite area. And I want to point out to you, let's say in this example here that I integrated from 0 to 1. If I integrated from 0 to 1, I would technically have a possible infinite area as we move up the vertical asymptote. So typically we distinguish improper integrals into 2 forms. One being, as we move to infinity, right, in essence like a horizontal asymptote, if you will, and then 1 being over a finite interval, right? If this, again, the limits of integration was 0 to 1, I don't have an infinity up here. 0 to 1 looks like it's a legitimate proper integral, but in the case of 1 over x squared, it's not, because at 0, I have a vertical asymptote. So usually, in a section like this in a textbook, you got to be a little careful. It doesn't have to have an infinity up here to be improper. You just have to make sure that there isn't a vertical asymptote. There isn't a division by 0 over your limits of integration. And that would be what we would call a type 2 integral. All right, so, I guess let's come back and look at the same example in that same light, right? And then we'll generalize some stuff here. So let's say we're looking at 1 over x squared, right? And we're going to go from 0 to 1. Right? So we're going to look at the integral of 1 over x squared, and we're going to look from 0 to 1, right? And again, let me see if I can switch to green. Here's 1, here's 0. We're technically looking at a possibly infinite area as we get close to this vertical asymptote. So what we would do in this scenario is we're going to back away from this asymptote. We're going to call that the number t. And we're going to take a limit as t approaches 0. So we're going to go, excuse me. I said we were going to back away from 0, and we're going to call that t. And we're going to take a limit as t approaches 0. Now if we look visually right here, we technically moved away from the 0, and we're going to approach 0 from the right. So this would be approaching 0 from the left. This is us approaching 0 from the right. So we really have a one-sided limit there. So we'll go from 0 to 1 of x to the negative 2 dx, and we've already evaluated this integral, right? So this is really, this is negative 1 over x as we go, in this case, from t to 1. So I'm going to look at, when I plug in the upper limit, I got negative 1 over 1, and then minus negative 1 over t. And again, we're taking the limit as t approaches 0 from the right. Now, if we think numerically, right, as we approach 0 here, the fraction is going to explode. It's going to become unbounded. It's going to go to infinity. Right? And again, numerically, right, if I let t go to 0, I have 1 over 1 is 1. 1 over a half is 2. 1 over a quarter is 4. 1 over a tenth is 10. 1 over a hundredth is 100. 1 over 1,000 is, 1 over 1,000th is 1,000. So as this gets smaller and smaller and smaller, this thing goes off to infinity. So this thing becomes infinite. So what we actually end up with is an integral that is infinite, right? Now, some textbooks will say that this does not exist, and that's totally fine. Some textbooks say, well, yeah, technically the limit, in terms of the epsilon delta definition of a limit, technically the limit doesn't exist. But some textbooks get a little lazy and they say, well, you know what, I mean, conceptually, right, or I should say conversationally, it's going to infinity, right? So in terms of the epsilon delta definition, it doesn't exist, right? But it's infinite. So in the language here, we're going to say the integral diverges. All right, now again, if we're interpreting this integral as an area, what we have just calculated is that the area, under the curve 1 over x squared from 0 to 1 is infinite. So we can't measure that area. It's immeasurable. So, again, as a student, I always thought this was kind of cool, right? I mean, so from 1 to infinity, the curve 1 over x squared has finite area, but from 0 to 1, the area is infinite. That is really interesting. All right, let's take a look at a couple more examples here. So actually, before we do that, let's generalize what we just saw. All right. So typically, we call this a type 1 and type 2. So let's do a generalization here. So basically, visually speaking, if I'm looking at, let's say, a curve where I go to infinity, right? And I have possibly infinite area, right? So let's say we're going out to here, right? So let's say we're going from a to infinity. So if I have the integral from a to infinity of some function f of x, right, then this is improper. And so what we would do in that case is we would go from a to t, and we'd take a limit as t goes to infinity, right? So that'll be our approach, right? Again, what we technically do is we back away, we pick a number t, and we let t go to infinity. And then we could really look at the same scenario going to the left, right? So, oops, I forgot to write up here that this is what we would call a type 1. This is a type 1 improper integral, right? So again, type 1's basically being, I have a horizontal asymptote, right? So if I look at this guy and I look at some function f of x, let's say I have that, right? And then I am considering possible infinite area, let's say from a to negative infinity, right? So then we would look at the integral of f of x from negative infinity to some number a. We're going to write that as t to a, and the limit as t approaches negative infinity. So those are the two integrals we would call type 1. And then type 2 would be a vertical asymptote. So type 2 would basically be, vertical asymptote here. So let's say, visually I could have something like this. Let's say I have a vertical asymptote, right, on this side, let's say. And we're looking, let's say from, let's say from B to A, and there's a vertical asymptote at A. So we're looking at the integral from a to b of some function, and we have the vertical asymptote at a. So we're going to back away from a, and then we're going to approach a. Now again, in this case, we're approaching a from the left, so we're going to back away over here, and we're going to let t approach a from the left, from the right. I said that wrong. We're approaching from the right. So, and then again, we could be looking at the other side. I don't want to have to redraw this all over again. So bear with me here. All right. So let's say I have a function that has a vertical asymptote. It doesn't matter where my vertical asymptote is. Right? If my area is moving upward or my area is moving downward, it doesn't matter. This is still possibly infinite area. So let's say let's call this the number c. Right. So I'm looking from c to a, and we're looking at possibly infinite area there. Right. So in that case, the integral of f of x from, let's see, we're going from c to a, and a is the vertical asymptote. So we're going to say that's the integral from c to a, and we're going to take the limit as t approaches a from the left. Right? So we're taking our vertical asymptote, we're moving away, and we're approaching the a from the left. So these technically would be the two. Actually, there's one other. So think about this for a second. What if I am going from C to B? So what I would have to do in that case from C to B, I would actually have to break this up into two separate integrals. I'd have to go from C to A and then from A to B, because I have possibly infinite area through both of those regions. All right, so a third scenario, and you got to be a little careful with these because sometimes this division by 0 is hidden inside the interval, right, of integration. So let's say I'm going from C to B there. Let me use the color red. So I'm going from C to B of f of x dx. So technically, I got to break this into two. Right? I got to go from C to A, where my vertical asymptote was, and then from A to B. So then this integral I would treat just like we did this guy. I would have to look at so approaching, you know, and I made a typo here. This was us backing away, and we are letting t approach a from the left. All right, let me make sure I'm fixing that properly. So if we're going from C to A, we're backing away from the A, and t approaches A from the left. So we're going from C to A, we back away, and we let t approach A from the left. If we're going from A to B, we back away from the A, we let approach A from the right. So there's that guy. So this integral here, our interval is passing over the vertical asymptote. The vertical asymptote lives between C and B. So we'd have to split that into two integrals. Now, what we'll typically denote in this case is we have to look at each of these integrals separately. Right? So I'm going to look at this integral, and if it diverges, then I stop. And I say the entire original integral is divergent. If I look at this integral and it diverges, I stop and I say this entire integral is divergent. Or if I look at this first integral and it converges, then I still need to come over here and look at this integral. If it also converges, then I say the whole thing collectively converges. If, this converges and then suddenly I find out this diverges, then I stop and I say the whole integral is divergent in that case. All right, now I want to look at a couple other examples here. You know what, let's look at an example of this last situation that we just looked at. Right? So let's say we're looking at the integral of x over x minus 2. And we're going from 0 to 5. So again, when we look at this problem, we initially don't notice that it's improper, and we don't see 0 to infinity or something of that nature. Right? It's not blatantly obvious, but we can notice that at x equals 2 there's a division by 0. Right? So there's a discontinuity at x equals 2. So x equals 2 has a discontinuity. I can't spell today. And keep in mind that falls in our limits of integration. Right? So we're going from 0 to 5, and that falls in there. Now, so I don't have to carry the limit process around with me all the time, I'm just going to get a little more efficient, and let's just find the antiderivative, and then we'll split this problem up as we need to. So when I look at x over x minus 2, a couple different ways to attack this integral. Probably what I would do is I would let u equal the denominator so that I get a 1 over u form. And then my du is 1 times dx. So my dx is equal to du. My dx is equal to du. And then I guess the issue here is I have an x left in the numerator. So this could be a little creative here, and I could solve for x here and say u plus 2 is x. So I'll put u plus 2 in the numerator. So the advantage here now is I could actually split this up. Or I could write this as u over u plus 2 over u. And then, u over u is 1. So the integral of 1 is u. And then this is the integral of 1 over u, which is ln of u. All right, so, I'm going to drop the plus c because we technically have limits of integration. So let's plug back in for what our u was. So we had x minus 2, and then plus 2 ln of x minus 2. And then we're going to evaluate this over our limits of integration. But let's come back for a moment and keep in mind that we have a discontinuity at 2. So again, I'm going to get a little sloppy here, but the integral from 0 to 5, we're going to have to break into the integral from 0 to 2 plus the integral from 2 to 5. And we're going to have to look at each of those separately. Remember, like we just talked about, this first integral converges, supposedly, right? Let's say that happens. Then I move to the second integral. And if that integral converges, we conclude the whole thing converges. But if either one of these integrals diverges, then we stop and we say the whole integral is divergent. Right, now keep in mind, for this first integral, I'm going to go from 0 to t, and I'm going to let t approach 2. And then, I'm going to be approaching 2 from the left. Right, so we already did this integral. Right, we said that this was x minus 2 plus 2 ln of x minus 2. So we're going to go from 0 to t, and we're going to take the limit as t approaches 2 from the left. Right? So when I plug the t in, I'm going to get the limit. So I'm going to have t minus 2 plus 2 ln of t minus 2. So there's my upper limit, minus, and then when I plug 0 in, I'm going to get 0 minus 2 plus 2 ln of negative 2. So there's with my lower limit plugged in, right? I'm going to take a limit as t approaches 0 from the left. Now we can see over here on the right-hand side, right, when we plugged in the lower limit, this is all finite values, right? ln of 2 is a decimal value, so 2 times that is a decimal, and then, minus 2, right? So this is all just a finite value. So the real question is, what's happening here as t goes to 0, right? Excuse me, that was not t going to 0. Why do I keep writing that backwards? I apologize, you guys. I'm still on Monday time. Right? So this was t approaching 2. Right? This was t approaching 2 as we wrote. This was t approaching 2. Right? All right, so now that we've corrected my statement there, so t is going to approach 2. Right? So I'm going to have basically 2 minus 2 plus 2 ln of. All right, and what I'm going to write here is pretty bad, mathematically speaking. So when I look at this, right, this is really something approaching 2. So what I'm really getting is like the ln of 0. I'm really getting the ln of something that goes to 0. That's really what I'm looking at. So inside, when I plug the 2 in for t, I get the ln of something going to 0. That's what I'm ending up with. Right? And we know from the graph of the logarithm that that is an infinite value. So if I think of the logarithm, here's the graph of ln of x. As our domain value approaches 0, the graph shoots to minus infinity. So this whole thing right here shoots to minus infinity. So our whole integral is, in essence, divergent, right? So we have divergent because it's not a finite value, right? Not finite. Limit doesn't exist. Limit does not exist. All right, so we only did one of the two integrals, and we found that it was divergent. So since that first integral diverges, then we're done. And we say the whole integral diverges. Right? So I could say the integral from 0 to 5 of x over x minus 2 diverges. So these couple examples here are illustrations of basically the type 1 and type 2 integrals that you would see in pretty much every calculus book. All right, so mathematically speaking, right, let's finish this conversation. So typically what we would do at this point is we would lead ourselves to what we call the comparison theorem. And in order for us to utilize the comparison theorem, what we want to be able to do is compare to a function where its behavior is known. And so what I mean by that is usually we look at a basic form of an integral 1 over x to a power. So what we're going to do is we're going to consider the integral of 1 over x to some power. Right? Now in our first example, the power was 2. We did 1 over x squared. In our last example, we basically did 1 over x to the 1. So basically what we're going to do in this scenario is, let's say we're looking from a to infinity, and we're looking at 1 over x to the p. Right? Now if you think about this, as long as p so when p is 1, then the integral of 1 over x is ln of x. Right? Again, I'm getting kind of sloppy here. This is not rigorous mathematically. Right? But I'm getting ln of x, right? From a to infinity. So when I plug the infinity in, again, oh my god, that's horrible mathematically. I'm breaking all kind of rules. Right? This is really a to t, and t approaches infinity, right? But if the inside approaches infinity, from the logarithmic graph we just got, that was infinite. And that diverges. So we know that when p is 1, this integral, 1 over x, diverges. Now what if p is not 1? Right? So here's what we're going to do. Let's break that up into two cases. Let's suppose p is greater than 1. So like our first example, p was 2. We had 1 over x squared. So when we had 1 over x squared, what we did was we rewrote it as x to the negative 2, and we evaluated that antiderivative. So, we add 1 to the power, we divide by the new power. We're going to go from a to infinity, right? Now, if you think about this for a moment, in our original example of 1 over x squared, once we had, x to the new power, it was negative, right? So if p is 2, this is negative 2 plus 1, which is negative 1. If p was, if this was 1 over x cubed, right, this is negative 3 plus 1, which is negative 2. So the numerator will always have a exponent that's negative when p is greater than 1. So when we had, let's say up here we have, pretend it's x to the negative 4, we push that to the denominator, we write it as 1 over x to the 4th. So what we really have in this scenario is, let's say, 1 over negative p plus 1, we have 1 over x to the, and remember when we push it in the denominator, we change the sign of the exponent. So this becomes p minus 1 when I change the sign of that exponent, and I'm going from a to infinity. And again, let's stop focusing on the letter p. Let's keep in mind this is a numerical value. So, if p is negative 5, negative 5 plus 1 is negative 4. So this is 1 over x to the 4th. And what happens to 1 over x to the 4th as I plug in infinity? I'm getting 1 over something that gets larger, and this goes to 0. So it turns out this is convergent, right? When p is greater than 1, the integral from a to infinity converges. So that's true for any value of p, right? If p is 2, 1 over x squared from a to infinity converges. If p is 10, 1 over x to the 10th from a to infinity converges. Even if p is, pi. All right, let's pretend p is irrational. P is pi. 1 over x to the pi, 3.14 is greater than 1, so that's going to converge. Right? 1 over x to the square root of 7, right? Whatever this number is, as long as it's greater than 1, it's going to converge. And then if we look at when p is less than 1, we're actually going to get the opposite result. So let's say we look at, x to the negative p from a to infinity, and again, we're going to add 1 to the power. We're going to divide by the new power. Now, again, numerically speaking, right? Let's suppose p is less than 1, right? So let's suppose p was negative 3. Let's pretend for a second p was negative 3. So I have x to the negative of negative 3 dx. Right, so that's the integral of x to the 3, which is 1/4 x to the 4th. Right? So when the p is less than 1, whenever the power is less than 1, what we actually end up with is something that's polynomial. And when we go to infinity, that's going to blow up. Right? So x to the 4th goes off to infinity. So this is just a specific example, right? But that's going to be true for any value less than 1. Whenever p is less than 1, then this exponent turns out to be positive. And since this exponent is positive, I don't push it into the denominator. It stays up here in the numerator, and therefore it diverges. Right? So we basically have, we could collapse this one and p equals to 1. So right, remember when p equals 1, it diverges. When p is less than 1, it diverges. When p is greater than 1, it converges. So we have this kind of final summary. We say the integral of 1 over x to the p as we go from a to infinity, right? If p is less than or equal to 1, that diverges. And then if p is greater than 1, it converges. So we have this generalized result that involves 1 over x to a power. Okay, so what that allows us to do is something like this, right? So let's say we have an example and we're being asked to determine if an integral converges or diverges. So let's say we're being asked to determine x over x cubed plus 1. Determine if x over x cubed plus 1 from 1 to infinity converges or diverges. All right, so if we look at evaluating this integral, that's a nasty technique of integration. In fact, I don't even know if I could find that antiderivative analytically. That would be pretty ugly. So what we're going to do is use a comparison theorem. So here's what we're going to do. We're going to focus on the integrand for just a moment. We're going to compare this integrand to one of the 1 over x to the p forms. So this is called basically utilizing the comparison theorem. So we're going to do the comparison theorem. So basically we're going to look at our original integrand x over x cubed plus 1, and we're gonna say, well, listen, our upper limit of integration goes to infinity. So as the upper limit goes to infinity, right, as x goes to infinity, then what we're going to say in this scenario is the numerator is dominated by its leading term and the denominator is dominated by its leading term. So as x goes to infinity, in the denominator, the plus 1 ultimately becomes, negligible. So we get infinity cubed plus 1, which is basically infinity cubed, right? So in the numerator, the leading term dominates the numerator, and the denominator, the leading term dominates down there, any other smaller degree terms. And so this function behaves like 1 over x squared. So this is basically be what we call determining whether the integral converges by the comparison theorem. So we would say the integral of x over x cubed plus 1 is approximately behaving like the integral of 1 over x squared. We had 1 to infinity on what I wrote. Okay. And then this is a convergent since p is greater than 1. So then we would deduce that our integral converges. So our integral, right, integral of x over x cubed plus 1 converges by the comparison theorem. Man, that is a sloppy converges there, right? So that integral converges by the comparison theorem. All right, so that pretty much wraps up any standard section on improper integrals. And I see you guys in the next video.